Screencast-O-Matic started. We are now recording. And we're going to current slide. But before we do that, I may even turn on the projector this morning. I think we paid this power bill, so I can afford to do that. Did want to let you know this. I've announced it before. Just want to make sure you know. The informational sessions concerning the institutional scholarships and summer Pell will be today. Both campuses, same time, both campuses, 11 to 1 and 5 to 6:30. Now, all those on this campus are in the faculty staff dining room. I showed you where that was, right? Okay. On the Birmingham campus, they're in the Leon Kennedy Center, the Student Center, in the cafeteria, which I think is going to make it pretty interesting because lunch is served 11 to 1. And I take it that's probably a pretty popular place then. I've seldom been over there for lunch, but it seems like it's pretty busy. But I bet you they'll get a corner somewhere and have the information session. And maybe pulling people who are eating lunch, so that might not be a bad idea. 5 to 6:30, that will be during the evening meal, but I think that's a lot less populated, so that shouldn't be an issue there. The faculty staff dining room, hardly any faculty or staff ever use that as a dining room, so that shouldn't be a problem there. Okay. Math team's always looking for more people to participate and have fun with them. They meet Fridays at noon and Mondays at 3 on the Birmingham West Campus in the Science Building, C Hall C100.
Not this Friday, though, because we're going to the Hell Mount Power.
Oh, okay. So they're not going to meet this Friday. Okay. All right. That sounds like a good trip. I know Mr. Rossi asked me if I wanted to go. I'd like to go to it, but I have a feeling I've got another meeting. Someone told me this morning that we might be in Huntsville Friday, so I've got to check and see if I'm on that one. Tutoring. I think I've announced this to you before. If y'all need tutoring, which I doubt, it's there, available, but I would highly recommend you look into becoming a tutor because y'all are prime candidates for that. And I need to give this to Nicoma if she comes in. Well, I've killed all the time I can. Any questions on anything we've done so far? All right. Now, this starts the converse of Theorem 3.8. Of course you remember Theorem 3.8, right? Yeah, you were looking at it on your things, but if not, you would remember. Let's just go back and do this. Theorem 3.8, and I think I mentioned this before. If C, f of C is a point of inflection on the graph of f, then either f double prime of C is equal to 0 or f double prime of C doesn't exist. Just like it was for critical points on the first derivative test. But just like it was for critical points on the first derivative test, that doesn't mean that just because f double prime of C is equal to 0 or f double prime of C doesn't exist, that it's automatically a point of inflection. It may not be. Remember, to be a point of inflection, it has to be that the way they express it, the tangent line crosses the curve at that point. The better way to look at it, or to me, the way I look at it, is if it is a point of inflection, then it's going to change concavity. It'll be 0 or not exist there, but it's going to change on either side of it. Okay. And the Nicoma's back, right? Okay, Diamond's back. I'm sorry, I said Nicoma. I was looking for her Diamond's back. Okay. All right. Now, so to be at a point of inflection, you have to change concavity on either side of that point. And just because it has a 0 or not exist, it may be the same on either side of that, so that wouldn't be a point of inflection. Okay? That's what this is saying. The converse of Theorem 3.8 is not generally true. Often it is, but it's not always true. That is, it is possible for the second derivative to be 0 at a point, and that point not be at a point of inflection. Here's an example. The graph of f of x equal x to the fourth. Okay? To determine if it's a point of inflection, what would you do?
Figure out where it's equal to 0 or doesn't exist.
Or what is equal to 0?
Or the, what do you call it?
Second derivative.
Yes.
Okay, yeah, of course. Okay. So the first thing you do is, good answer. Take a derivative. Okay. So let's do that first. Okay. What is f prime? Whoa, let me get my pen activated. Okay. F prime of x is equal to
4x to the third.
4x to the third. Okay, now that's not going to tell us much about second derivatives. I mean, about points of inflection. So what must we also do?
Set it equal to 0.
Well, that to give you your critical points. And we'll do that, and that's only 0 at x equals 0. Okay, so yeah, first derivative, potential extrema is x equals 0. Only one. But to get points of inflection, what must we do?
Take a second.
That second derivative. So f double prime would then be 12x squared. And set that equals to 0, or places it doesn't exist. This is a good old polynomial function. Everything exists everywhere, so that's fine. And where that's equal to 0, where? At x equals 0 again. So, is that a point of inflection? The second derivative is 0. It's a candidate to be a point of inflection. Or if the second derivative didn't exist, that would be a candidate to be a point of inflection. Is it? Well, they've drawn the graph for you, so it sort of takes away the mystery of it. But what you would have to do is do something to a little bit to the left of 0, like x equal
-1.
-1. -1 squared is
1
times 12 is
1.
times 12. Okay. All right. Positive, meaning the second derivative is concave up, coming in from the left. So take a point on the right. X equal 1. 1 squared is times 12 is 12. Okay. And that's also positive. So it's concave on the right. I mean, concave on the right. Concave upward on the right. Concave up on the left, concave up on the right. Obviously here is concave up everywhere, including at your position where the second derivative is 0. So that's not a guarantee that you'll have a point of inflection. You've got to have that equal to 0 not existing for it to be even considered as a point of inflection. But just because it's 0 or doesn't exist doesn't guarantee it will be a point of inflection. So it's concave up on both intervals. So it's concave up at, well, they technically don't say it's concave up at 0 because its second derivative is 0 there. It's flat there, okay? That's all you can say. But it's up on either side, so it's concave up everywhere. Okay?
So pretty much any even power function won't.
Okay. I would say any power function greater than 3. 3 or greater. If you do the second derivative, even if it's odd. Oh, wait. No, you're right. Yeah, because, odd, is going to be curved the other way. So, every even function, power function, even power, the pure power functions, if they're even, they're going to be, because they're all shaped like parabolas. You're right. Okay? All right, good deal. Now, we lead to the second derivative test. They like naming these tests, but you know what? What you're going to find is, if I'd only had a V8, if I'd only known that, I could have saved myself some effort before. in addition to testing for concavity, which is one thing a second derivative does for you, it can be used to perform a simple test for relative maximum or minimum. Okay? Now, just flash back to doing our rational our relative maximum, relative extremum. What did we do? We took the first derivative, set it equal to 0, and the values for x, whether that was either equal to 0 or not defined, those were your critical values. Just like we just did for second derivatives, they may or may not indicate a local extremum. But those are, it's got to be there if it's 0. Okay, how do you say this? It can't exist unless it's either 0 or not defined, but just being 0 or not defined doesn't guarantee it's going to be an extremum. Okay? So what we did before, once we found those critical values, you knew it was either 0 or doesn't exist then what we did was test it on the left and the right to see if it's above or below that, and if it was above in both places, it's a minimum. If it's below in both places, it's a maximum. If it's above in one and below in the other, it's a neither. Okay? Guess what? If we had only known about the second derivatives then, what you'll do, the test is based on the fact that if a graph of a function is concave upward at the point containing C, and it's a critical point, then it must be a minimum. Because if it's upward at C, it's got to be that way. So it's got to be a minimum. Downward at C is going to be a maximum. If it's 0 at C, we don't know. Then you have to go back and do your test. Okay? So rather than testing points, if we'd have just taken the second derivative before, evaluated at C, found out if it's positive, negative, or 0, positive, that means it's a local minimum. Negative is going to be a local maximum. 0, you have to go back and test. Okay? All right. Similarly, if the graph of a function f is concave downward on an open interval containing C, then f prime of C, and f prime of C is 0, meaning it's a critical value, then f of C must be a local maximum. So if it's concave, if you know your first derivative is 0 there, that makes it a candidate for a critical value. If it's concave up there, then that means it has to be a positive second derivative there. If it's concave downward, meaning a second derivative is negative, but it's a critical value, the first derivative is 0, then you have to be a local maximum, relative maximum. Okay. So it would really make this thing a lot easier not to have to test. But if it's 0, you still have to test. Okay. So here is the theorem 3.9, which is the second derivative test. Let f be a function such that f prime of C is equal to 0. That means C is a critical value. Okay? Doesn't mean you have a local maximum or minimum there, but it's a candidate for that. Okay? Can't have a local maximum or minimum unless it's either 0 or not defined. But just the fact that it is 0 or not defined does not guarantee it's a local maximum or minimum. Okay? So rather than testing, what we're going to do is take the second derivative of f, and if that exists on the open interval containing C, then if that is positive, that's a relative minimum. If it's negative, that's the relative maximum. Don't have to test. If f double prime of C is equal to 0, this test fails. That is, f may have a maximum, minimum, or neither. Ends up, you go back and test. Pick a point on one side or the other of C and see what it's doing. Okay? If both of them are less, it's a maximum. If both of them are more, it's a minimum. And if one's above and one below, it's a neither. Okay? So you may still have to do your testing, but only if the second derivative is 0. All right, so let's do example 4. Find the relative extrema of f of x is equal to negative 3x to the fifth plus 5x cubed. What is the first thing you're going to do? Take a derivative. Very good. F prime of x is equal to negative 15. Second, x to the fourth. Plus 15 x squared. Now, what do we do with that? All right. If you're looking for relative extrema, we're looking for our critical values. Okay? Critical values are one of two things. What are they?
Where it's equal to 0 or doesn't.
Okay. So the first thing we're going to do is take that first derivative, minus 15x to the fourth plus 15x squared, and set it equal to 0 to see if we can find our critical values. Or if it didn't exist. But this is a good old polynomial function that exists everywhere. So we won't have any that don't exist. Okay? So what are we going to do there? Factor! Excellent. And what will you factor? A little louder? Yes, and a little bit more. Go and factor out the 15 with it. Okay? And, since it's leading off with a minus sign, get that too. Okay? So this will be minus 15x squared, greatest common factor. What's left in the first term? X squared. In the second term? Second? Okay. Did I hear a sign with it? Minus 1. Okay. And that's equal to 0. Okay. Are you through factoring? No. What else can you do? Don't forget your minus 15x squared. You're through factoring that. I mean, sure, you could do 3 times 5 times x, and with a minus somewhere out there, you know. But that's not going to give you anything new. Let's leave that monomial alone. But what about the next part? Plus 1 times x minus 1, and that's all equal to 0. Now here you have 3 factors, or more if you wanted to, that are equal to 0. What does that mean?
3 critical numbers.
Second?
3 critical numbers.
Okay, and what are they?
0, 1, and negative
X equals 0, x equal 1, and x equal negative 1. Everybody see those? Without having to go through and do all the algebra? Okay, those are your 3 critical values. Okay? Now, we have 3 potential extrema. Okay? Now, the next question is, are they extrema? What we did before was pick something to the left of negative 1, and between negative 1 and 0, between 0 and 1, and something to the right of 1, and evaluated their first derivatives at each of those places, which was sort of time consuming. Now we've learned an easier way. Now I've told you, mathematicians are inherently a little bit lazy. To be a good mathematician, you have to be, right? Because they're always trying to find the easiest way to do a problem so they don't have to work as hard, right? Now, any of you qualify as good mathematicians? No, you're all hardworking. That's okay. You can still do it, okay? But if you're a little lazy, you have an edge up, okay? So, what are we going to do next then? Okay, f double prime of x. Now, what the book did when they were doing this one is they factored that one to the right of f prime. And then I would have thought, ooh, then they're going to do a product rule. But no, they went back and used this. So that's why I separated those 2 pieces out. Let's just use this one. That's so much easier to take a derivative of than the product rule. I mean, product rule is easy, but this is easier. So what do we have here?
negative
60
third
x cubed
plus 30x.
30x. And actually, you don't have to do anything else to this one. If you are looking for points of inflection, yeah, then set that equal to 0, then factor that, then go to town on that. We'll do that, okay? But we're not looking for it. All we're looking for is relative extrema now. So what we're interested in is what? Plugging in. So we plug in f double prime of 0. And what would that be?
0.
What does that tell you about extrema?
It's probably the minimum.
It's what?
It's probably the minimum.
No, it tells you nothing. Because with 0, it's inconclusive. Only if it's positive or negative does it tell you whether it's an extrema. You can't tell from second derivative if it's equal to 0. It may be a point of inflection. We don't even know that yet, okay? We'll come back to 0. How about f double prime of 1? What would that be? Negative 30. And we really don't care what the value is. It's negative. So that means what? X equal 1 is a concave down, meaning x equal 1 is a local concave down. Yeah. Maximum. Okay. So this is I like to say local. They use relative. Okay. So it doesn't matter. A relative, goodness gracious, a relative max. Okay. And f double prime, oh, this is inconclusive. Okay. F double prime of minus 1 would then be what?
30.
Positive 30. Okay. Which means relative min. Okay. Okay. So we saved ourselves having to do something to the left of minus 1 and something to the right of positive 1, but that's all we saved. Okay? What we've got to do still is find something to the right or left of 0. Okay? And which do you want to do? It's sort of up to you. You could go back to the original function and do something just to the left. Don't go as far as negative 1, like negative 1/2 and positive 1/2. And you can either plug it into the first derivative, the function, the first derivative, or the second derivative. Okay? You can go any of the places you want to and see what you get. Okay? So, what you want to do, plug into the function, the first derivative, or second derivative. I don't care much.
Plug it into the second derivative.
Okay. Okay. Even though the coefficients are bigger, you have smaller powers. Okay. I'll go with smaller powers. Okay. So let's do f double prime of negative 1/2. Okay. Using this, that would be a minus 60 times what is negative 1/2 cubed. Negative 1/8. Okay. Plus 30 times a negative 1/2. Okay. And this will be a positive 15 halves. Is that right? 4 will go into 60 15 times. 4 will go into 8 2 times, right? Okay. Minus 15, right? Okay. 15 halves minus 15. I really don't care the value, though we can calculate that. I want to know the sign. Who wins? The negative. So this is negative, and it happens to be negative 15 halves, okay? Okay. Just happens to be that. So that means to the left of 0, you're concave down, right? Okay. Let's go to the right of 0, f double prime of 1/2. And that would be minus 60. I say 60 and write 16. There's something dreadfully wrong with my brain, okay? Okay. 60 times, what is 1/2 cubed? 1/8. Positive, okay? Plus 30 times 1/2. And what does that give you? Same number as before, it's just different sign. Negative. Well, yeah, ultimately, negative 15 halves plus 15, which will be positive 15 halves. And what does that tell you? This is concave down, this is concave up. Okay? So, does that tell you whether you have an extrema there or not? Down over here, up over here?
Tells you that you don't.
You do not have an extrema. This is a neither. Okay? But it does tell you it's a point of inflection because your concavity changes there. So that's another good reason to use the second derivative, because that if you're interested in concavity, a point of inflection, that tells you something. Okay? You know that it is a potential point of inflection because the second derivative is also 0 at 0. Okay? And this tells you it is a point of inflection. It changes concavity path across that 0. Okay? Not guaranteed that it would. This one does. Okay? So the relative extrema are at 1 you have a relative maximum, at -1 you have a relative minimum, and at 0 you don't have an extreme value, but you do have a point of inflection. Now, we didn't see if there were other points of inflection. We just know that at 0 you do have a point of inflection. How would you tell if you have any other points of inflection?
Test more.
Second?
Test more points.
Do what?
Um,
Test more points? You like to work too hard, okay? All right. Budding mathematician, but you like to work too hard, okay? Here's what you do. To tell if you have a point of inflection, just like to tell if you have extrema, set the first derivative equal to 0. To tell if you have a point of inflection, set the second derivative equal to 0. Or where it doesn't exist, but that exists everywhere. So what we'll do is come over here and do minus 60 x cubed plus 30 x is equal to 0. And what would you do next? Second? We've already found all the derivatives we need. What we were trying to do there, here you have an equation. Factor! Very good. Okay, and what would you factor? Second? Okay, I would take out the sign too. Minus 30x. I don't like having leading negatives. I just don't, okay? It's okay to have them, I just don't like it, okay? And what do you have left? Second? 2x squared minus 1. Okay, equals 0. Now, the sad news is this tells us that x equals 0 is a potential point of inflection. We've already tested and know that it is a point of inflection. So I already know that one. Okay, x equals 0, point of inflection. PT of IN, point of inflection. Okay? Now, we've got two more, and they're not differences of two perfect squares unless you consider the first one to be the square root of 2 times x. And that would be, then, a perfect square. Okay? And the comments here. Now, I have something for you. I don't know, you may have already seen it. You had pre-registered for Cal 2 this summer, right? But they opened it up before I had the schedule in. So the time was wrong. And because I knew I was going to see you, or thought I'd see you the next day, I went on and changed it for you. Okay. Will Monday, Wednesday, 11 to 1:40 work with you just as well as the other time? Okay, that's what you schedule. Okay. I think I did for some of the others of you too, but I've already given you that form. Or I got it done before you pre-registered. Okay. So, there's a couple ways you can do this. Here's what we're testing. 2x squared minus 1 equals 0. And for some reason, the 2 decided not to print. Okay, so the 2x squared minus 1 equals 0. How would you go about solving that one?
2x plus 1 times x minus 1.
Okay, you think that'll work? 2x plus 1 times x minus 1. The 2x squared certainly will work. Oh, it won't work, will it? Because you have a minus 2x and a plus x. You'd have a middle term. Good try, but no cigars, okay? Any other efforts? When you don't have a linear term, you can just go on and solve it for x squared. Add 1 to both sides, and that gives you 2x squared is equal to 1, right? And then divide by 2. Okay, wipes that out. So x squared equal 1/2, then take square roots. X equal plus or minus the square root of 1/2. Which you can also write as, let me write it somewhere else, x equal plus or minus 1 over root 2, because the square root of 1 is 1, okay? Or, if you don't like that form, you could write that as plus or minus root 2 over 2. I don't care how you do it, but some way, those are your other two possibilities, okay? Now, are those relative, are those points of inflection? Okay. Now, what we have so far, the only way to tell is evaluate it on either side, okay, of root 2 over 2. Anyone happen to know what root 2 over 2 is, approximately? Pretty close to 0.7, okay, because root 2 is about 1.414, you know, that, and 2 is 2. And that will go into about 0.7 times, okay? So you could do, say, 0.7 on one side and 0.8 on the other side, see what you get, okay? And probably the second derivative would be the best place to do that. The math is a little nasty, but all you're interested in is the sign of it. And if the sign changes on either side of this 0 for the second derivative test, then you have a point of inflection. If they're the same sign on both sides, then no, you don't. You will find, I think, that both of those are points of inflection. Now, what I'm real tempted to do is say, go on and take a third derivative and see. Now, we don't have a name for that, but if the third derivative is positive, then it's a good chance you'll have positive or negative. It's a good chance you'll have a point of inflection. If it's 0, then yeah, it probably won't. But we haven't done that test. So right now you would go and plug in. Okay. Or if you have a graphing calculator, you would give it to Jeremy because he just came. No, you wouldn't. Okay. What am I saying? Okay. All right. So, you know you have one point of inflection. We have two others we can check. And it's pretty easy to check by plugging in. Like I said, sub-value just to the left and the right of each of those. So that would be, like I said, 0.7 and 0.8, or negative 0.8 and negative 0.7. So it's going to be in between each of those. See if your concavity changes. If it doesn't, if it's same on, if it changes across that, then you know you have a point of inflection. Okay. Now, let's clear all this out of the way. Any questions before I clear it? What we were doing? Okay. So let's see what they do. Begin by finding the first derivative of your function. And again, like I said, here they found it just like we did, and then they factored it. Okay? Now, it's fine to do that and saying both of those are true. But when you go to do the second derivative, don't think this is the easier form. That's the easier form. The only reason they're factoring is to set it equal to 0 to find out what the potential critical values are. That's why they factored. So I like to do that as two separate operations, but you can do it at one. Okay? From that derivative, you can see that x equal -1, +1, and 0 are your three critical values, critical numbers. But we don't know if they're local extrema until we test. And the easiest way to test is to find the second derivative, which you do from this form, and then factor it just like we did. And then we plug in those three values to see what happens. At 0, this will be 0, so you have no conclusion there. But at -1, this will be negative, and this will be negative. Okay? So that will be positive. So that means you have a local minimum there. Okay? At +1, that'll be positive. That'll still be negative, so you have a local maximum there. Okay. Now, the test fails at 0, though. Now, if you like these little tables, do the little tables. Okay? Perfectly fine to do so. Okay? Now, here's another thing, folks. Like I said before, you can plug in values on your original function, which they did, which is not a bad idea to do. You plug in the x up here at -1, that would be 3 minus 5, a negative 2. So -1, -2 is a point, 0, 0 is a point, and 1, 2 is a point. Okay? Now, if you just think about this, -1, -2, 0, 0, +1, +2, guess what, team? That has to be a minimum. You would think it doesn't have to be. The odds are it's going to be a minimum. The odds are that's going to be a maximum, and the odds are this is going to be a neither. Because how do you get from here to there, through there, without having another extreme in the way? Now, you can't guarantee these are. They can be points of inflection that don't have a chain, a local minimum or maximum. Could be, okay? So you do have to still check them. But the fact that you're here and here, that gives you a really good idea. This one in the middle is not going to be an extreme. If it was an extreme maximum, it would have to turn back around to get up here, or it gives you a clue, okay? All these things work together. So they actually evaluated the points -1, -2 by plugging in your critical values to your function values, okay, 0, 0, and 1, 2, okay? And then the second derivative being positive tells you that it has to be a minimum. Second derivative being negative tells you it has to be a maximum. You can almost guarantee you can't get from a minimum here and a maximum here and have this being anything but a point of deflection, okay? You can see that. So you didn't really have to do your second derivative test again because you have values over there. It can't get there unless it's one of those. I just realized I left something on the board overnight, which means it'll probably not erase. Oh, I did a little bit. Okay. That one was left overnight and it won't erase, so I got to get my cleaner out here and clean it. Okay. So, here's, because the second derivative test fails at 0, 0, you can use the first derivative of the test to observe if f increases to the left or right of x equals 0. Guess what? You already have it, don't you? Okay? You have it decreasing to the left of 0, 0 and increasing to the right. Just from those points up there, you didn't have to do anything else. Okay? You could tell that has to be a, it can't be an extreme value at 0, 0. It has to be a point of inflection. Well, no, you can't. Yeah, I think you can guarantee that as well. Nah, yeah, I'm debating that, but I think you have a pretty good shot at it. So here is 0, 0 is neither a relative minimum or maximum, even though the graph has a horizontal tangent line at that point. The graph of f is shown here, okay? And as we saw, the second derivative is negative all through here, meaning concave up, positive here, concave up. It becomes, it has a point of inflection here. It's concave up here, concave down there. There was that point of inflection that's at negative root 2 over 2, negative 0.707. Right there is that. You can't tell where because you know it's concave up here, you know it's concave down there. Somewhere in between, and that would be about 0.707. Point of inflection there at 0, 0, because it's concave down here, concave up there. And because it's concave up here and concave down there, somewhere in there, it has to be a second derivative of 0, and that would be a 0.7 at the square root of 2 over 2. Okay? And then it's concave down forever, so the second derivative is negative from there on that. Make sense? So, first derivative tells you where you have horizontal tangents. Second derivative, or not, okay? Horizontal tangents for sure. Where it's equal to 0, that gives you your horizontal tangents. It doesn't tell you whether that's a minimum, a maximum, or neither until you do the second derivative test. If it's concave, if the second derivative is positive, it's concave up, making it a minimum. Second derivative negative, concave down, making it a maximum. Second derivative equal to 0, you can't tell, okay? But then, when you also have a second derivative of 0 here and here, if it's concave up here, 0 there, so the positive second derivative here, a 0 second derivative there, you have to change signs somewhere. Positive, it has to be 0. Oh, I see, no, you really need to do the whole test. I was trying to think if it's a shortcut. Sometimes you can't get enough shortcuts. So anyway, but when you look at it, you see concave up, concave down. So you had to have one in there. Concave down, concave up. That has to be a point of inflection. Concave up, concave down. Has to be another point of inflection there. And we know the values. Negative point, square root of 2 over 2, and positive square root of 2 over 2. And those are points of inflection because they change concavity there.
Whoa, that's the last example in the section. Yeah. Now, I think I've given most of these homeworks before, but let me say them again. Do number 3. Do any of the odds 5 through 15. And number 3 and those odds are at calcchat.com. Number 13 is at calcview.com. Do any of the odds 17 to 31. They're all at calcchat. 17's at calcview. Do any of the odds 33 to 43. They're all at calcchat. 37's at calcview. Do either 45 or 47. They're both at calcchat. Neither one of them are at calcview. You can take a look at 49. That looks like a pretty good one. That's a calcchat. I hope it would be that. Then number 51. It's a calcchat. Excuse me, not a calcview. Then do either 53 or 55. They're both a calcchat. 53's a calcview. Then you can think about 57. Yes, that's a think about it. Do it if you would like. It should be at calcchat. There's a conjecture at 59. You can conject with that if you want to, or not. It should be at calcchat. Sort of an interesting little problem, number 61. Try to do that. It's pretty interesting, okay? 63 is pretty much an applied problem, and that should be fun too. And then from then on, any of the odds, in fact, I guess I should go back and say, do any of the odds, I'd say, do any of the odds 65 through 70, well, no, 65 through 65 or 67. Do either one of those. They both should be at calcchat. Then do either 69 or 71. They should be at calcchat. And then do 73 if you can. That's a pretty interesting problem. 75 and 77 are true-false. Don't expect to see any of those on a test, but there's still good things to think through. And 79 is a proof, so if you are into doing proofs, go for it. Okay. Now, limits at infinity. It seems like to me I debated on whether we should do that. A summary of curve fitting, I believe, would incorporate everything we need. And I don't think we're going to do optimization problems there. Fun problems, they're a good deal. Are any of you going into industrial engineering, maybe, or thinking about it? If you are, that's something they really do a lot of in industrial engineering, trying to find places where you have greatest efficiency. That's optimization problems. They're sort of fun to do, but they do take a bit of effort to do. Wow, this is a long chapter. I really do want you to look at Newton's method. And let's see. I think we're going to have to cut our losses here because we're running out of term and we got some more material to cover. So the limits at infinity are not bad. And in a real sense, you've already done that back in pre-calculus algebra when you talked about the end behavior. That's what you were doing. So it doesn't have the calculus applied as much, but I think we're going to need to skip that. However, don't skip the section. As you page through this, you see the nice little blurb here on Maria Gaetana Agnesi, okay? One of a handful of women to receive credit for significant contributions to mathematics before the 20th century. 20th century, okay? All that time, there were some good women mathematicians, but either they weren't allowed to pursue their education, or they had to do it on the sly, or people still didn't take them into account. She's one of the ones that did get recognized. It wasn't easy, though. Okay, so just want to point that out in case someone doesn't have a paper topic, hint, hint. There's about fewer than half of you have turned in a paper, and we're running out of term, as mentioned earlier. Okay, so let's go on to 3.6, a summary of curve sketching. Okay, so let's go on and end this, and discard that, and end that, and end that, and go to 3.6. I put all these out there. I think I put them on Blackboard so you can go and see the PowerPoints and stuff, but I think we're going to have to skip that one. We lost those days early in the term, remember, weather and things like that, so we just are a little, and I draw things out too much. So let's look at applications. The chapter is applications of differentiation, and this section is, oh wait, let me get the slideshow set up. That's why it's not looking right. Okay, summary of curve sketching, 3.6, and what we're going to do is analyze and sketch the graph of functions. Let's do these fairly quickly if we can. When you're sketching the graph of a function, either by hand or with a graphing utility, remember that normally you cannot show the entire graph. Okay? The decision as to which part of the graph you should choose to show is often crucial. So, for instance, when viewing the windows of a function here, f of x is equal to x cubed minus 25x squared minus plus 74x minus 20. Here's something to notice. Notice those huge coefficients, except for the leading one. That means you're going to have some pretty wide variation in this. And if you don't choose your window properly, you may miss tons of information. Okay? So here, if you're looking from -2 to 5 and -10 to 40, it looks like a parabola, doesn't it? It's not. Okay? If you expand that to -10 to plus 30, and then also expand your y's big time from -1200 to 200, then you see you got a lot more stuff going on. That's probably the basic of the thing. And how do we know that? Remember in pre-calculus, leading term test. Now your books probably call it leading coefficient test. I like to call it leading term test. That means what's your end behavior? If there's an x cubed there, it starts negative, goes positive. It starts negative, goes positive. That lets you know this starts negative, but winds up going negative. So that's not the whole picture. That probably is. Other things you can tell is the has up to 3 zeros. 1, 2, 3 zeros. There aren't any more. Don't keep going out here. It's just going to keep going negative. Don't keep going out there. It's just going to keep going positive. You have your 3 zeros. Okay? Other thing we know, n being the degree of the polynomial, 3. N minus 1 is 2. 2 turning points. The most you can have. There's a turning point. There's a turning point. There aren't any others. It's not going to flip around and do anything else, so this will let you know. So, just your pre-calculus will let you know some things. End behavior, maximum number of zeros, maximum number of turning points. You don't have to have that many zeros, and you don't have to have that many turning points, but once you've reached that, don't look any further. You can't have any more. Okay. So, pre-calculus algebra can help you there. Okay. By seeing both views, it's clear that the second viewing gives a more complete representative of the graph. Because you look at this one, all you're seeing here, and you're not even seeing it very well, you're seeing
something from here to there. I mean, that's all you see is that. That's what this is showing. It kind of looks like a parabola, but it's not, okay? Because you didn't have a big enough view. Expand it out, and you see this is just a tiny little piece of that. But looking at the second one, are you still seeing enough? And the answer is yes, you probably are, because of your end behavior, your number of zeros, and your number of turning points. That convinces you, yeah, going any further is just going to show me more negative here, more positive there. Okay. Would a third viewing window reveal other interesting portions of the graph? Not knowing what we know. To answer this, you need to use calculus. Nah, you can just use your pre-calculus to interpret first and second derivatives. Okay? To determine a good viewing window for a function, use these guidelines to analyze its graph. Okay? Determine the domain and range of the function. So far, most of them have been polynomial functions. What are those? All real numbers. Now, your range isn't always all real numbers, but it's potentially all real numbers. Okay? Now, if you said something else like sines and cosines, yeah, they're not going to get outside of some window this way, plus or minus a, right? So don't expand your y forever. You're never going to use it. Okay? You might, and then they repeat themselves, so you wouldn't need that either. Okay? Determine your intercepts, asymptotes, and symmetry of the graph. Okay? Now, in your text, the asymptotes are in section P1. We didn't do P1. You can go back and check on that. Okay? Symmetry was also in section P1. We didn't do. Domain and range was P3. We didn't do. But that's all. I mean, all those are things from pre-calculus. Like I said, that was pre-calculus. You have all you need. Oh, our 10 o'clock scholar. Justin's here. Good. All right. Good deal. We're starting 3.6. I'm sorry. 3.6. We skipped 3.5. Okay. Now, locate the x values for which f prime and f double prime are either 0 or do not exist. For f prime, that would be your critical points. For f double prime, those would be the potential points of inflection. Not guaranteed, but potential. Use the results to determine relative extrema and points of inflection. Yeah, that's what first derivative gives us. Candidates for relative extrema. That with the second derivative tells us whether they are or not, or still may be unknown. Points of inflection, second derivative, and maybe a little more work. Okay. So, and by the way, then you have your differentiability is 2.1, relative extrema is 3.1, increasing and decreasing function 3.3, concavity 3.4, points of inflection 3.4, and then the things we just skipped, the horizontal asymptotes and infinite limits at infinity. We're both in 3.5. If you need those, go back and review those sections, okay? But horizontal asymptotes, how you get that? Ratio of leading terms of a rational expression. That's what you look at. That was pre-calculus. Infinite limits at infinity, just plug in some big numbers and see if they just keep getting big. It's not, and your end behavior, that gives it to you as well. So let's do example 1. I guess that's what's next. Yeah, here it is. Analyze and sketch the graph of f of x is equal to 2x squared minus 9 over x squared minus 4. Okay? Now, some of this probably was in the section we just skipped, but you had it in pre-calculus too. What kind of function do we call this? Hint. It's a ratio of two polynomial functions. So what kind of function would we call it? Take that word ratio and expand. Rational function. It's a ratio of two polynomial functions. Okay? Now, let's do a quick analysis of it. Okay? What are some things you can do right off the top to talk about the sketching? And this is all pre-calculus stuff. Okay? All right.
Can't have 0 in the bottom.
Say again?
You can't have a 0 in the
Okay, that's a good observation. So let me get my pen set up. Oops, I already had my pen set up. Let me get my color set up. So we know that x squared minus 4 cannot equal 0. Right? That's what Clark just told us. What values of x would make that 0? Say again? 2 and negative 2. X cannot equal 2, and x cannot equal negative 2. Now, if x can't be something, what kind of a situation does that give you?
domain.
Vertical asymptotes, exactly. Okay? So if we're analyzing and sketching the function, here we'll go 1, 2, negative 1, negative 2. Now, I'm going to intentionally change my color. Okay? Right there. You've got it. Your denominator can't equal 0. Anywhere it equals 0, you have a vertical asymptote. Now, I say that, let me back off just a bit from it. In this problem, that's true. Because in this problem, you're fully, if you factored everything out, you wouldn't be able to cancel a thing out. If you had a fairly complicated looking rational expression, you factor the denominator, factor the numerator, you say everywhere that denominator is 0, but if one of those factors existed in the numerator too, cancel them out or divide them out. Now you don't have a vertical asymptote there. What you have there then, that x would be a hole in the graph. Okay? If it can't be factored out or divided out, then you have a vertical asymptote. If it's common to numerator and denominator, you're going to have a hole in the graph there, not a vertical asymptote. Okay. But, yeah, good. Good observation. What are some other things you can observe about this? You remember that from pre-calculus algebra? Some of you should, because I think I know who you had, and I think I know whether you did it or not. Okay? But I didn't have all of you, so. Anyone remember anything else you can do? Here's just a hint. Clark zoomed in on you can't have a 0 in the denominator. What if you had a 0 in the numerator? What does that tell you? Anything? Say again? A little louder. Okay, no, numerator can have zeros in them. Okay? But if you had a numerator with a 0 in it, what does that tell you about the function? It's what? It's got to be a 0, doesn't it? If either 2 was 0, which it's not, or this thing was 0, which it could be, then your whole function is 0. But what happens, what is your f of x? Y. And where y is 0, that gives you what? Second, you call them either one of two things, solutions or x-intercepts. So sure enough, where your numerator is going to be 0, that's going to give you your x-intercepts. Remember, that's one of the things that's helpful to have. And where is your numerator 0? Anyone want to look at that and let me know? Say again? Yes. So here's your two x-intercepts. 3, 0, because the y is 0 there, and negative 3, 0. So we can go on and plot those points. Okay? Right there. These are intercepts. Do you know the function crosses the x-axis there? And those are the only two places where it's equal to 0. Okay? Oh, good deal. Okay? Anything else you remember from pre-calculus algebra? We got a vertical asymptote. Well, wait. Let's do it because it's real easy. We got your x-intercepts, 3, 0, negative 3, 0. What's true about the y-intercept? X is equal to 0. And that's pretty easy to do, isn't it? What happens if you plug x equals 0 in here? What do you have as your numerator?
0.
Really?
Negative 18.
Negative 18, your denominator? Negative 4. So you have your y value when x equals 0, the y value is going to be negative 18 over negative 4, which I can simplify to be 0, negative over negative is positive, divide both by 2, and you get 9/2, right? There's your y-intercept. Now, how many y-intercepts could you have? Could you have ever had 2 or 3 or 4? No, because it wouldn't be a function, would it? Fail the vertical line test. The y-intercept is a vertical line, okay? So you can only have one y-intercept. You may not have any if that was your horizontal, a vertical asymptote, but 9/2. So 9/2 is 4.5. 1, 2, 3, 4.5. So there's your y-intercept, okay? I can almost tell you what's going on right there. You know this can't be coming down here, can it? Because if it did, you'd have another 0. And you don't. So it can't cross or, this, so this has to be going up. Here, I've just sketched part of the graph there with 1 point, okay? And knowing that you don't have an x-intercept there. Good deal, huh? Okay, yeah, I can tell you're excited, okay. Now, we've got our x-intercepts, our y-intercept, our vertical asymptote. What's one thing we're missing? Horizontal asymptote. Does anyone remember how to get that? I already snuck the words in earlier. I don't know if you were listening.
The leading coefficients.
Yes, the ratio of your leading coefficients. And your leading coefficients is 2x squared over x squared. I mean, not coefficients, leading terms. 2x squared over x squared. What's that ratio? 2. So y is equal to 2 will be your, let me go back to red here, your horizontal asymptote. You may not have a horizontal asymptote. This one does, and it's going to be there. Get out of there. Okay. That's not talking to you. Okay. Now, you guess what? Believe it or not, I can graph the rest of the function. Okay? It's not really fair, but guess what? This is all from pre-calculus. Okay? You know it's got to, in the long run, be approaching the x I shouldn't have crossed there. And here it's going down here. Here it's going down here. And here it's going there. There it is. Now, I don't have it exactly. Okay? I don't have anything precisely. But I bet you that's going to be pretty close. Okay? Just based on what we have. If we didn't have a point here, you couldn't tell. Okay? But with the points there and with that point there, yes, you can tell that. Okay? Now, have we used a bit of calculus so far? No. Okay. If you wanted to use some calculus, you could take some first derivatives and find out where your critical points are. And I bet you from my graph, you're only going to have one. 0, 9/2. Okay? That's the only place where you're going to have a horizontal asymptote. I mean, a horizontal. First derivative is 0. Okay? You want to do it just to see? Okay. I was hoping you'd say no. Okay, f prime of x would be what? And guess what we got to use on this? The what? You probably will, but the major rule you got to use is the quotient rule. Our favorites, right? How does that go? Low to high. So the low is x squared minus 4. Derivative of the numerator is now, I appreciate that they had factored this out for you, but really to do your derivatives, you need to multiply it through 2x squared minus 18, right, over x squared minus 4, okay? So what's the derivative of the numerator? 4x. What's the next part? That's the low d high. Minus what? It's high d low, right? Yeah. So it'd be 2x squared minus 18. D low is 2x over low x squared minus 4 squared. Okay? Now to set that equal to 0, who cares about the denominator? We know x can't be plus or minus 2 anyway, so forget about that. For this to be 0, the numerator would have to be 0. So I guess we got to work that out. What's that numerator? That's going to be 4x cubed minus 16x minus 4x cubed plus 36x. Okay, right? Did I do it right? Okay. Now we're going to set that equal to 0, right? But guess what? Oh, nice! Those x cubes disappear there, don't they? And then what do we have left? 20x equals 0. It's the only place that's equal to 0? Not that hard. Where's that true? 20x equals 0.
At 0.
At x equals 0. You can divide both sides by 20 and you get x equals 0. What did I tell you? There's your only horizontal tangent. Okay? Now we don't know that's an extremum except by our reasoning earlier. We don't know it, but let's check it and see. So how could we check that? We took our first derivative, hint, hint. Take the second derivative. Okay, now, so let's see. What is that first derivative again? It turned out being 20x over x squared minus 4 squared, right? Because we simplified that numerator, just multiplied through, distributed, and all that kind of stuff. That's what it came out to. Even before we set it equal to 0, it came out to that. So now, how do we take a second derivative of that? Unfortunately, what rule? Quotient rule, okay. And how does that go? Low, so that's x squared minus 4 squared times 20, that's d high, minus 20x, that's high, d low. And what's d low here? 2 times x squared minus 4 times, here we do use a chain rule, 2x. Okay? That, I think, is it, folks. Okay? Over low, which is x squared minus 4 to the fourth power. Okay. Now, all we're interested in is what the sign of this is right now at x equals 0. Okay? The sign at x equals 0. So x equals 0 here. And by the way, x equals 0 here, the denominator is positive, right? Negative 4 to the fourth power. Anything raised to an even power is positive, right? Okay. So we know that the denominator is positive. Let's deal with the numerator. X equals 0, negative 4 squared is? Positive. Okay. Positive, okay? And positive times this is positive. And it will be 3,200, by the way, right? 16 times 20, 3,200, right? So positive, okay? And x equals 0 here, that's going to be 0. That has a, that's just 0, right? So this is positive, meaning concave up and local minimum. Okay. So all you need to do, you don't need to do any more calculations in it. That gives you that. And it's that way. Is that at 0? We've already shown it can't come back down again, so it's going to be that way within your limits there of plus or minus 2. Because you see, at x less than minus 2 or greater than positive 2, this is still positive, right? Because you're raising the number to the fourth power, that's going to be positive. But let's see what happens over here. With x equals, say, 3, okay? Then this will be a positive number times a positive number, that's positive. This will be, this is equal to negative 3, I said. That's going to be positive. That's going to be negative times a negative. No, times another negative. So it's 3 negatives, that's going to be negative. Okay? And over here, that would be a negative, negative, positive. So, I'm sorry, I said that backwards. And the negative 3 here, this would be a positive times a positive times a negative. So that makes that negative. Over here, that would be a negative times a positive times a positive. That's still positive. So it's concave down here, concave down here, concave up there. Okay. So we used our derivatives. They didn't tell us anything much more than what we already knew, right? But you can use them, okay? Should use them. That's what we're in the course for, right? Okay. So that and if you look at what they did, domain is all real numbers except x equal plus or minus 2. Yeah, we did that when we saw the zeros there in our denominator. Range, you had to almost draw it before you could find that. It's anything from negative infinity up to 2, and then from 9/2 to positive infinity. But you had to do that by drawing it. I mean, you couldn't do it any other way. X-intercepts, we found those pretty easily. Y-intercept, we found that. Vertical asymptotes, we found those. Horizontal asymptote, we found that. Symmetry with respect to the y-axis. Now, we didn't talk about that, but what tells you that that has to be symmetric about the y-axis? An even function. Your x's are all to the even powers. So it has to be symmetric about the y-axis. So whatever's happening here is happening there, here, there. Okay? So yeah, that wasn't essential, but it's true. First derivative, yeah, we found that. Second derivative, yeah, we found that. Critical number, we only had one, x equals 0. Possible points of inflection. Oh, we didn't do that one, did we? Forgot Forgot to do that. Possible points of inflection. Again, that's taking this numerator and setting it equal to 0. Let's see what we get when we do that. Sorry, I forgot that. So here we have, oh man, do we want to do this. Yuck. No wonder they just said none. Okay. You would have to multiply all that stuff out. Oh man, I really don't want to, but let's do it. That would be x to the 4th minus 8x squared plus 16, all that multiplied by 20. Minus, here we have a 2x, a 2, and a 20, so that's minus 80x squared times x squared minus 4, right? So that's not too bad, okay? We're setting it equal to 0, so we forget about the denominator. That's not going to affect us at all. So here we have 20x to the 4th minus 160 x squared plus 320 minus 80 x to the 4th plus 320 x squared. And we're going to set that equal to 0, right? Do I ever dislike doing this? Okay. I think that's going to be a negative 60 x to the 4th plus 160 x squared plus 320 is equal to 0. And since I don't like leading off with a minus, I'm going to multiply by minus 1. I hope this is legal. I think it is in most states. Okay. Make it like that. Okay. Now, what I would do next was, well, factor out what you can. I know a 4 will go into all that. I think that's about all we've got. So when you factor 4 out, that would leave you 15x 4th minus 40x squared. I could have taken a 10 out. Let's take a 10 out. Okay. Sorry about that. And then factor out a, okay, I should have done that. Okay. Dumb. Okay. Then factor out a 2. And you got a 3x to the 4th minus 8x squared minus 16 equals 0. You agree so far? Okay. Now I will use quadratic formula and say x squared is equal to minus b, which will be 8, plus or minus the square root of b squared, which would be 64, minus 4 times 3 times a negative 16. Right? If you can read that, good luck with that. Now that's interesting, because I was hoping that was going to come up something you can't do, but you can do it. 64, no, I'm sorry. You have 2 minuses, so it's going to make it a plus. So that's going to be I feel like I've done something wrong and I can't quite see what it is. how can they just say possible points of inflections, none? Let's go back and try factoring that. I was going to not do it, but let's try it. 3x to the squared minus 4 times 3x squared plus 4. Will that work? Well, to me this isn't worth taking that much time on. We already know what it looks like. I just can't see how they got the possible points of inflection, none. I look at it and say, yeah, there aren't any. The only two possibilities are where they don't exist. The second derivative doesn't exist. And that may be what all this would lead to. I don't know. I think I may have made a sign change, so I don't want to tie up too much more time with this. They do some test intervals. I don't think you need to do those. We've already done it. So let's move on. If it's, well, okay. Let's see if they tell you any more. I'm going to erase all we got here. And let's see what happens. Domain, all real numbers except, yeah, we did that. Range, we did that. Actually, we did it from our graph. X-intercepts, we did that. Y-intercepts, we did that. Vertical asymptotes, we did that. Horizontal asymptotes, we did that. Symmetry with respect to y-axis, we did that. First derivative was that. Second derivative was that. Critical numbers x equals 0, the only one. Possible points of inflection. Ha! Why didn't I look at that? I've already erased my stuff, so sorry about that. Looking at the second derivative in the factored form, that's what I forgot to do. Okay? In the factored form, we could have gotten rid of one of those. Yeah. It's almost worth going back to it. Let's do it. I was dumb. Let's do the second derivative again. Here they give it to us, but let's do it again. F double prime of x is equal low x squared minus 4 squared d high times the 20 minus high 20x d low, which is 2 times x squared minus 4 to the first power times 2x, okay, over x squared minus 4 fourth, okay. This is what I failed to do, okay. Notice here we have a common factor of x squared minus 4 in numerator and denominator. So let's get rid of that one altogether, and that makes, and make this a 3 down here. Dumb move on my part. And what does that give you? 20 times x squared minus 4 minus $80x, okay, over x squared minus 4 cubed, okay. And then if we multiplied this out, that would give you 20x squared I think we did some of this, but 20x squared minus 80 minus 80x. No, I made a mistake somewhere, because that's what we're getting. So on this we can, and this is all over that denominator, and this would be a 20 times this last one was 80x squared. Sorry about that, because it has 2 x's in it. So sorry, making so many dumb mistakes here. Okay. that would be, this is over that denominator cubed. Okay. This will be a minus 60x squared minus 80 over that denominator, which would be a minus 20 times x squared plus 4. 3x squared plus 4 over x squared minus 4 squared. Yeah, that's what they got. Okay. Now, there's where, yeah, okay. I had made some stupid mistake somewhere. This is what that is. You set that equal to 0. This will never equal 0. Ever. Okay? So that's why they can just immediately say positive points of inflection is none. I didn't simplify my second derivative. That's what you need to do if you can. And that shows you this thing is never equal to 0. It doesn't exist at x equal plus or minus 2. So those are your two possibilities, but we're concave down, concave up, concave down. But they're not defined there, so you can't have it there. Okay, so you got it. That's why you can say that. Sorry I missed that one. Okay. Let me erase my chicken scratch. They did do it right. And test intervals, you don't really need them. You got everything you got. If you got your vertical asymptotes, your horizontal asymptotes, your things. If you had some of those places you didn't have a point, yeah, you need a test interval. But we had a point outside you see, this is outside the first asymptote. These two are both between the first asymptotes. The two asymptotes, and that's outside the second one. Well, goodness gracious, you already have your, they haven't shown it yet. Okay. Well, or did they on the earlier one? You already had your y, yeah, they already showed it. And that gave you everything you needed. So you really didn't need a test interval. You have a point in every interval, and you can't do otherwise. So what they do here is in the first interval, they calculate your function, your first derivative and second derivative, but they didn't really calculate it. They said it's decreasing concave downward. I guess, they did calculate. They found that it was, they didn't do the function, but did first derivative, second derivative, negative, negative, decreasing down. Okay. And then x equal negative 2, nothing's defined. Between negative 2 and 0, first derivative is decreasing, second is negative, second derivative is positive, so that means you're decreasing but concave upward. And then x equals 0, you have a value there, 9/2, and your first derivative is 0 there means you have extremum, and then your second derivative is positive there, which means it's concave. It's a relative minimum. So why did you need, see, this line right here negates the need for these lines here. It told you nothing. Once you know the second derivative is positive, at that point, it has to be going up. You did not need those other two. Concave up, you have it. Vertical asymptote, there, undefined, yeah. You got everything you need. Okay. There's the graph. Doesn't look too far from what I did, with a lot less work. Okay? All right. A graph of a rational function having no common factors. Remember, that was a key to it. And whose denominator is of degree 1 or greater, which means not a constant denominator. Okay? Degree 0 or fractional, I guess. Okay. Has a slant. Has a slant asymptote when the degree of the numerator exceeds the degree of the denominator by exactly 1. To find the slant asymptote, use long division. In this one, you could use synthetic division. Rewrite the rational function as a sum of a first degree polynomial, the slant asymptote, and another rational function. Okay? So that's Where is this coming in? Oh, okay, I guess this is example 2. Okay. And there's an example of that, okay? So let's do this. Do you remember how to do your long division or synthetic division of polynomials? Oh, no. Oh, don't tell me you don't, okay? Let's do long division first. X minus 2 into x squared minus 2x plus 4. And by the way, why are we even doing this? Yesterday, I pulled my computer off, so I have to check. Okay, the degree of the numerator is exactly 1 more than the degree of the denominator. It's the only time you do this. If that was a 3 and a 1, don't bother with it. It's not going to tell you anything. If it's a 2 and a 3, no, it's already, yeah. Only if the degree is, if the degree is the same, you don't do this. If the degree more than 1 degree more, don't do it. Only if it's exactly 1 degree more. Okay? So now we'll do this. And this is pretty easy. X will go into x squared how many times? X times, right? Then multiply. X times x is x squared minus 2x. Right? Whoa. Then you subtract. Just like you do long division of numbers. Do y'all remember how to do long division of numbers? Or has it been too long? You've been using a calculator too long, right? Let's do a long division of numbers. Let's do 12 into 124. How do you do that?
12 goes into 12
one time, then you multiply, right? Subtract. Bring down the 4. Divide. 0. And then your remainder is 4 over 12, which is 1 over 3. Right? We're going to do the same thing here. Divide first, and you divide left to right. Everything else you do right to left. Division you do left to right. So x will go into x squared x times, then you multiply just like we did there. You subtract, everything goes out, bring down the 4, and that doesn't go any time, so your remainder is plus 4 over x minus 2. Okay? Now, what does that tell you? You have a slant asymptote of x. So you go over here to the graph and do y is equal to x. There it is. Your identity function, right? Y is equal to x. Okay? And then your vertical asymptote is the x equal 2, right? Because that can't be 0. So there's your vertical asymptote. So the function is there and there. Okay? They didn't give you any points. You really should have chosen 1 point. And a real easy one would be, we'll set x equals 0. And x equals 0, that 0, that 0, and what you have? 4 over negative 2 is negative 2. And there it is. So there you have this part, because you can't cross your asymptotes. So you have to pick a point up there. Let's pick it x equals 3. 9 minus 6 will be minus 3 plus 4 is 1 over 1. Oh, that's not right.
That'd be 7.
9 minus, I can't add. 9 minus 6 is 3 plus 4 is 7 over 1. So it's 7. Yeah, you're right. So if x equals 3, y is equal to 7. Okay, now that doesn't give you the lowest value, but then you know it has to have that shape. Okay. Sorry, I can't have it. Not in a hurry anyway. Okay. I'm really beginning to rethink whether we need to do this. I think it probably is useful. Do y'all think so or not? Curve sketching? Huh? Gotta have it? Is that what you said? Okay. So we'll pick up with example 3 next time. I'll try to go a little bit faster and try not to make as many dumb mistakes. Okay.
Sort of helpful in thinking about it. Or
Yeah.
Learning how to analyze.
Okay. Oh, we don't have that much more to go. So this is a short section. Then we're going to skip 3 point. No, I'm sorry. Oh, yeah. We'll skip 3.7, too bad, and then we'll go, I think 3.8 is Newton's method. I want you to see that, okay? And, ooh, we still got to do differentials. Okay. We'll try to get as much as we can.